we can have even more complicated collisions. For example, let's say we have a disk, and the first one has radius r1, and it's rotating with speed, with angular velocity omega 1, in the clockwise direction. And then let's say we have another disk. We'll call it disk 2 with radius r2, and it's speeding clockwise, with an angular velocity omega 2. So the first one's going counterclockwise, the second one's going clockwise, and let's say they're moving toward one another, and they both have equal mass, and they both have equal velocity coming towards one another. Okay, so afterwards they're going to collide and stick together, and then we can imagine that this whole thing, after they've stuck together, is going to begin to rotate around their center of mass, which would just be right in the center in this case. So let's calculate what that would be. So we're going to assume in this case that, again, well, actually, we don't have to assume that whether omega 1 or omega 2 is bigger. But remember, when we're working problems like this, we always choose the positive direction to be the direction that things are rotating. And so our positive direction in this case is clockwise. If you remember using the right-hand rule, that's what we would get. Which I don't really talk much about in the videos, but your book talks about it, and I think does a good job describing it. So I would recommend, making sure you read that part of the chapter in your book. So the initial angular momentum then we see is just the moment of inertia of the second disk times its angular velocity, and that's a negative. That would be negative, right? Because this one's spinning clockwise, and then the first disk is I1 omega 1, and this one's positive because it's spinning counterclockwise. Okay, and then afterwards, right, the final angular momentum is going to be the moment of inertia of the first disk times omega final plus its mass times its radius times its final angular velocity plus the moment of inertia of the second disk times the final angular velocity plus its mass times its radius squared. And so remember, the reason that we have this other term is because we're having to use the parallel axis theorem, right? So the first one's rotating around this point, so this is where this is its center of mass, but it's actually rotating around this point that's shifted a distance r1 from its center of mass. So we have to make sure we account for that here, and so that's where this second term comes in, and we have that for both of them. So we see that we have omega final outside of moment of inertia 1 plus moment of inertia 2 plus m1 r1 squared plus m2 r2 squared, and that's going to be equal to I1 omega 1 minus I2 omega 2. So the final angular momentum is I1 omega 1 minus I2 omega 2 all over I1 plus I2 plus m1 r1 squared plus m2 r2 squared. And so this would give us the final angular velocity. Okay, and so now let's say that the moment of inertia of the second disk times its angular velocity was greater than the first. Well, that would just mean that this is spinning in the opposite direction. That's going to give us a sign and tell us that this is going clockwise instead of counterclockwise, which is the way that we solve this. And so that's just a little bit more complicated than the system we had last time. And then I purposely gave these both the same mass and the same velocity, so we know that they would just stick together and spin around a common point at the origin. Whereas if one of them had a larger velocity or larger mass, then conservation of momentum would tell us that afterwards, then this whole system would start moving in some direction too. So you can see these problems can get really complicated as we get further into this.